Welcome, everyone. Thank you for joining today's webinar. We are excited to have the opportunity to share with you the information in today's presentation, which is titled Benefits of the New TruCount Multi-Turn Absolute Encoders. My name is Eric Rice, and I'm the moderator for today. This webinar is part of a series that we are offering over the next several weeks. If you've not already checked out the lineup of upcoming webinar topics, I encourage you to do so. You can find them on our website, appliedmotion.com. Questions about today's presentation are very welcome, and there will be time at the end of the presentation to answer those questions. You can submit questions using the questions box in the webinar control panel. Today's presenter is Mike Maroney. Mike has 15 years of experience in the motion control and medical device industries, including a total of 8 years of experience at Applied Motion Products. He's held various roles at Applied Motion, initially as a design engineer, where he focused efforts on our first field bus and integrated motor solutions. Then as the head of our application engineering department, where he led our team of engineers in solving challenging motion control applications of our customers. And most recently, Mike was promoted to a key role in our product management group, where he oversees many facets of product development, including market analysis, product roadmaps, development schedules, and much more. Mike holds a bachelor's degree in computer engineering from the University of California, Santa Cruz. And with that, I will turn everything over to Mike for the presentation. Mike, it's all yours.
Thanks, Eric. So today I'll be talking about our TruCount Absolute Encoder and explain a little bit about encoder technology in general, benefits of the TruCount, some application examples, and finally, I'll touch on product availability before taking some questions. Just a note, after reviewing the webinar feedback from our last presentation, I'm going to skew a little bit more into the technical details here. We really do read that feedback, so please let us know what's valuable to you so we can course correct as we move forward in this series. We'll start with the basics. What is an encoder? It's a position feedback device. At a very high level, there are 3 common types. An optical encoder. This is what most people think of when they think encoder. It's a clear disk with a series of black marks at defined intervals. Light shines through the disk, and the resulting pattern is decoded and position information is extrapolated from it. There's magnetic encoders. This is a magnet mounted to a shaft with a pickup chip located a precisely controlled distance away. The magnetic field changes as the shaft rotates, and the pickup chip converts that into position information. And finally, capacitive. This is a PCB with traces attached to the shaft and another opposing PCB, which is stationary. The induced RF field on the stationary track changes as the shaft rotates, and the encoder converts that into position. I'm not going to touch on the pros and cons of each technology here. That would need a lot more time to cover. That's just an ultra high level overview. So now let's look at the differences between incremental and absolute encoders. I'm going to use optical encoder disks for these examples just because they're the easiest to visualize, but the idea is the same regardless of the technology used. So in the disk on the right, there are 2 tracks. Let's call the outer track A and the inner track B. There's also a once per revolution track that we call the index pulse. As we rotate the encoder clockwise, the photosensor sees the A LED shine through the disk before the B LED, so the drive can infer clockwise motion. If we then change the direction of rotation, we see B turning on before A, so the drive can infer counterclockwise motion. The number of black lines on the tracks is the encoder resolution. If the drive knows how many lines are in one revolution, it can then calculate the velocity of the motor based on the time between pulses. However, at any given instant, the encoder really only has 4 states. So taken as a point in time, the incremental encoder is useless as a positioning device. It relies solely on the drive to track the number of pulses and therefore track the position. The exception here is the index pulse. Because there's only 1 index pulse per revolution, we know that if we see the index pulse, we're in a known position in 360 degrees. So let's take that concept a step further with an absolute encoder disk. Notice the changing pattern of LED ons and LED offs, ones and zeros. as the absolute encoder disk on the right rotates clockwise and then counterclockwise. The encoder has 8 tracks of positioning bits, and it's arranged in such a way that no given pattern repeats over the 360 degrees of rotation. Going back to CS 101, this gives us 2 to the 8th, or 256 unique positions around the disk. This allows us to, without context, look at the pattern of LEDs and know exactly where in 360 degrees the drive is, with a resolution of 360 degrees over 256 counts, or about 1.4 degrees per count. Now, you might be thinking 1.4 degree accuracy isn't very useful. That's often right. For many applications, it's not. The reason I use an 8-bit graphic here is simply because beyond that, it's challenging to see all the tracks clearly. A real single-turn absolute encoder like this one might have 15 bits of single-turn accuracy, but to the naked eye, it's just a blur after that first 7 or 8 tracks. But even with all the resolution in the world, this disk can only resolve the position within 360 degrees. What if you want to move more than that? You need to track how many revolutions the motor has gone from your initial home position. And to do this, we utilize something called a turns counter. Think of the index pulse as go in Monopoly. Every time you pass the index, you update the turns counter. For every index pulse encountered in a clockwise direction, the turns counter is incremented by 1. And for every index pulse encountered in the counterclockwise direction, the turns counter is decremented by 1. So if you want the absolute position, you simply combine the single turn absolute position, which is the pattern of LEDs from the previous slide, with the value in the turns counter, and all of a sudden you have your real total distance traveled from your origin. Now, those of you who have been around AMP products for a while might realize that AMP has done this for a long time. Our EP register tracks the total number of encoder pulses from the initial home position you set on power up. But what about when the drive is powered down? This is the key advantage of the TruCount encoder. It can track drive position against the home position set at some point in the distant past, like machine commissioning. It can retain that information across power cycles, and it can even track motion which occurs when the drive is powered off. So how do we retain that information? There are several approaches to saving position data on power down. The most straightforward is to simply watch your power supply, detect a brownout condition, and anticipate that you're going to lose power soon. Then you write the current position to non-volatile memory, and you're done. It's a great option if you're sure the load won't move during power down, but that's often an unrealistic assumption to make. For example, if you power down the drive during an STO event, you're almost guaranteed that the load will move as it freewheels to a stop. So with that in mind, we know we need to account for power down motion. There's a few common ways this is done. The first is mechanical gearing, and this is done by adding in a geared turns counter that increments a physical mechanism on every rotation. You can use a battery backup. This is a small battery, often in a cable assembly, that powers just the encoder and keeps the turns counter alive. The battery needs to be serviced at some intervals, and unplugging the cable accidentally can lead to position loss in some cases. And finally, a batteryless backup system can be used. This employs a unique energy harvesting device that provides a small burst of power on every rotation, which is just enough to update the non-volatile memory where the turns counter is stored. And this is the TruCount solution. So let's look at some specific tech specs. This is a batteryless, magnetic, multi-turn absolute encoder. It is 100% maintenance-free. We have a 16-bit turns counter, which means we can track the absolute position over 2 to the 16, or 65,584 revolutions. We have 15-bit single-turn resolution, which means we can resolve 32,768 unique positions in 360 degrees. And now that's a bit of an odd number if you're not used to powers of 2. So we made the default 20,000 counts per revolution to match our existing StepSERVO products, which brings us to another feature of the Applied Motion Products Integrated Motors, electronic gearing. Electronic gearing allows you to ignore the encoder position completely and set the number of counts per revolution to some number that's useful to you and your application. So let's dive into electronic gearing for a minute using a real product as an example. But before we get into the math, I want to plug our applications engineering team. They know this stuff inside and out, and they are happy to help you set this up for your machine. Okay, so say you have an ultrasonic sealing machine with a linear stage that you're using to set the product height for a run of these small bags of chips. Maybe these chips are 5.06 inches tall, but this is a shared machine, and the next product you'll be filling are standard larger size chip bags that come in at 11.46 inches. It's advantageous to be able to set the product height in some easily understandable units, both to reduce PLC coding complexity and especially to aid the maintenance techs who are going to have to sift through that code later when some problem appears. So let's say that our lead screw spec is 100 turns per inch, which means it takes 100 revolutions of the motor to move the load 1 inch. With that given lead screw spec of 100 turns per inch and our native resolution of 20,000 counts per turn, we can see using that first formula that we have a movement of 5 times 10 to the negative 7 inches per count, which is a lot more precise than we need here. Plus, it doesn't lend itself to intuitive programming and maintenance. We can define a distance unit based on a number of factors, but for right now, let's just say that we want to program our PLC in units of 10,000ths of an inch. That means for every motor count we command, we want the load to move 1/10,000th of an inch. Or, said another way, to move the load 1 inch, we would need to multiply the inches, we need to move by 10,000 counts. So with our bag of chips, we would just need to multiply the inches by 10,000 to get the absolute position we need for this product run. 5.06 times 10,000 equals 50,600. That's our position goal, and anyone looking at the code could easily convert it to inches in their head. So how do we convert that goal into an electronic gearing setting? Remember, we know our lead screw spec and our desired resolution, so we can simply rearrange the above formula to solve for counts per rev. That would be 1 over 100 inches per turn divided by 1 over 10,000 inches per count, which yields a desired number of 100 counts per revolution. So we set our electronic gearing in the drive to be 100 counts per revolution. Bear with me one more minute here, and let's look at a second axis with a different lead screw, and I'll tie it all together. So the left-hand column is the example from the previous page, with a 100 turn per inch lead screw leading to a 100 count per rev setting for electronic gearing. On the right, we see that we have a different 20 turn per inch lead screw used for line width adjustment, which we need because the different bag form factors have different widths, and it's important for them to be centered under the sealer without crushing the chips inside. If we sub in the new lead screw spec into the same formula, we yield an electronic gearing setting of 500 counts per rev for this second motor. Does this make sense? The new lead screw has 5 times fewer turns per inch than the original lead screw, and our equation tells us it requires 5 times more counts per revolution than the original lead screw to move the same physical distance. Does this check out intuitively? Yes. So with the formulas and checks done, we'll program our motors with the electronic gearing ratios we calculated, and we're off and running. Your PLC can now command move distances in a single distance base. So for the small bag of chips, that's 5.06 inches high by 1.25 inches wide. You can tell your height axis to go to position 50,600 and your width axis to go to position 12,500. And you could comment the code in your PLC or your HMI to say that the distance units are 1/10,000th of an inch per count. If we now do a product changeover to the larger bag, that's 11.46 inches high by 4.25 inches wide, those numbers become 114,600 and 42,500. Quick and relatively easy. If you ever need to reuse your PLC code on a different machine with different axes, or swap out the lead screws on an existing machine, for example, because you realized that 100 turns per inch was overkill for this coarse positioning application, and you could save a ton of money by moving to a 10 turn per inch lead screw, you simply recalculate the electronic gearing with the new lead screw specs, plug it into the integrated motor, and no PLC changes are required. Even your comments stay the same. Now again, none of this electronic gearing stuff is unique to the TruCount encoder. It applies to all Applied Motion Products drives. The real advantage of the TruCount comes in how absolute positioning ties in with the electronic gearing. But to make that work, you also need to tell the motor where to start measuring from. So let's start to look at that with homing. When you first get your integrated motor with the TruCount encoder installed in your system, you need to tell it where the home position is. Unlike a traditional incremental encoder, however, this home position is burned into non-volatile memory, so your motor will remember its home position power up after power up. Once you burn the home position into non-volatile memory, it'll stay there. And the encoder can combine the single turn absolute value, the position counter, and the home position to track distance from your origin point without any additional startup routines ever again. But if you need to change the origin point, that's also no problem. You can update the home position in non-volatile memory at any time. App Note 52, available on appliedmotion.com, walks you through the different methods you can use to set the initial home position. As with most of our configuration parameters, the easiest way to do this is with the StepSERVO ClickTuner software, but the app note does outline some other methods you can use as well. And again, our apps team is available for assistance in getting up and running with this. So now let's tie together the relationship between these three concepts: absolute positioning, homing, and electronic gearing. When you change your electronic gearing, what you're doing is you're changing the relationship between motor counts and the physical distance moved by the load. If you're at absolute position 1000 and you cut your electronic gearing from 500 counts per rev to 250 counts per rev, what should happen to your current position? What about your home position? Should the motor attempt to recalculate positions to keep the same physical home location as it was before? And if so, does that mean that your current position should be immediately cut in half? Should the limit positions scale down to be in the same counts position as they were before? All of these are valid approaches, but they're quite different in their implementation. Our approach is this: anytime you change the relationship between drive counts and physical distance, you need to reset the physical limits as well. And in practice, what that means is, if you change the electronic gearing, you must rehome the motor and you must reset the clockwise and the counterclockwise limits. All of this is covered again in App Note 52, and our apps engineers can walk through the procedure with you in detail. The TruCount encoder can add significant value to your projects in a number of ways, the most obvious of which is removing the need to home on power up. This allows you to have faster recovery from unexpected shutdowns, faster product changeovers and setup axes, guaranteed position accuracy on power up, and peak power savings when hard stop homing multiple axes. I want to talk about that last one for a minute. I had a customer who had a massive sorting machine that used about 200 axes as diverter motors, like this one. On startup, they were hard stop homing all 200 axes at the same time. Looking at their power budget, they realized that even though the motors individually were small power consumers, this hard stop homing period was driving their peak power consumption for the entire machine. The first idea was to space out the homing sequences to run more sequential smaller groups, but the startup time of doing that in series was rejected out of hand. Switching to absolute encoders was able to eliminate that homing sequence completely, which achieved the desired result of pulling down their peak power demand for their machine. It can really pay to look at your application constraints, identify the weakest links, and see if there's a drop-in way to address them. You can also see non-trivial cost and complexity savings with the removed need for external positioning sensors. This allows you to reduce PLC programming complexity, save panel space, reduce wiring complexity, and reduce system costs. There are a number of specific application spaces, such as setup axes and diverter motors, where absolute encoders are the obvious and in many cases the required customer choice. However, I would encourage you to take a hard look at your other applications and see if a TruCount encoder would add an operational edge that you don't have today. They can help free up cabinet space and reduce machine complexity by reducing external homing and position sensors and all the associated circuitry and redundancy those components pull through with them. And the TruCount's battery-less design means the maintenance piece traditionally associated with absolute encoders disappears. There's one other reason absolute encoders are often passed over in favor of incremental encoders, and that's cost. But with TruCount, the cost is the same as our incremental options. So let's look at where this is offered. Currently, the TruCount encoder is available off the shelf in our TSM23 and TXM24 integrated motors with both RS-485 and Ethernet interfaces. These are our IP20 and IP65 StepSERVO integrated motor models. With these models, we're able to support Ethernet IP, Modbus TCP, Modbus RTU, stored queue programs, streaming SCL commands, and all of our standard operating modes. You can place an order on appliedmotion.com today for these models. Coming soon, and shown in the 3D model on the right, the TruCount encoder will be available in our NEMA 34 frame size Ethernet StepSERVO motor, and those are the TSM34 and TXM34 families. And again, the pricing for the absolute encoder models is the same as the incremental models. We offer a wide variety of customized options, from small firmware changes through major linear actuator mechanical designs. For example, Profinet came up in the last webinar. That's one example of a custom firmware job that we've delivered. The TruCount encoder, offered off the shelf on the integrated motors I mentioned in the last slide, is another tool in our customization arsenal. If you have an application that requires a customized motor or an absolute encoder in an otherwise standard product, please reach out to your regional sales manager or our applications engineering team, and we would be happy to discuss it. And with that, I'm going to hand it back over to Eric for some questions.
Thanks, Mike. That was great. A number of questions have already come in, so we'll start with those. But as a reminder to everyone in the audience, if you'd like to submit a question, use the question box in the webinar control panel. So first question is, Mike, how much linear travel can the encoder track?
Yeah, so that depends on the linear stage you're using. If we go back to the specs page, let me see if I can find it here. So if we go back to the specs page, we see there's a 16-bit turns counter. So this is 65,584 turns, plus or minus 32,000, give or take. So your lead screw spec is going to define how many turns per revolution the physical load moves. When we go back to the electronic gearing discussion, we're talking about that. So it really depends on your linear screw. And our apps team would be happy to go through that with you.
Awesome. Okay, next question. Can you go back to the slide listing the motors? I think this is the slide listing the motors that it's available on. Yeah, I think that's the one.
Okay, yeah.
So maybe just
any question, or just want to see the slide again?
Yeah, that was the
sure.
question,
So right now it's available again on appliedmotion.com. You can buy them off the shelf in the TSM23 and TXM24 families in both our Ethernet and RS-485 options. So we can support a wide array of applications there. Soon it's going to come on the NEMA 34 models, and then following that on some of our other products. But we really do encourage you, if you have a product that would use this, that could use this, let us know. It might be on our roadmap already. We might be working on it. We might be able to develop a custom for you. We love custom projects, so we're happy to talk about any place you might need to use this.
Thanks, Mike. Let's see, next question. Is there a limit on how long the encoder can maintain position with power off?
No. And so let's go back to this comparison slide here. So with the battery backup encoder, there's a couple of ways that can be implemented. A rechargeable battery in the cable is a very common one. So the battery will wear down over time. It's usually a long period of time, but it wears down over time. And so if you don't turn the drive back on to recharge that battery, it can wear out. And again, those have a life as well. So there needs to be some maintenance piece where you replace that battery at some interval. With the TruCount encoder, it is completely batteryless. And the way that it works is it harvests energy on every rotation. So there's nothing in there that says after some amount of time, I'm not going to be able to harvest energy anymore. So it can be off, for years, and it won't care at all.
Okay, good. Thanks, Mike. Let's see. Do you plan to offer the absolute encoder on the MDX motors, the integrated servo motors?
Yes, we do. So the generation 2 of the MDX motor is in development now, and it has an absolute encoder on it. So the generation 2 motors will definitely have that. And again, talk to us. Reach out, talk to your RSM or talk to our apps team, and we can work with you.
Nice. Does the encoder require a second power supply?
The encoder does not require a second power supply. It is completely and 100% self-sufficient. It harvests the energy. So this is a magnetic encoder. So there's a magnet mounted on the shaft, and then there's a pickup coil that actually generates a pulse of energy on every rotation that powers the turns counter right. So it's completely self-sustained, self-contained and self-sustained.
Perfect. Okay, so we got a number of questions, Mike, about the NEMA 34 with the absolute encoder. So I think we're going to have to circle back on that. The people that answered that question, obviously that's there's some enthusiasm about that product. We don't have a hard.
Yeah, and we know there is, and that's why it's the next one in our development queue.
So that's a little bit of a teaser. So to everyone out there who's wondering how soon is soon, we'll answer that as soon as we can. That's about the best we can say right now.
It's
so
in prototype right now.
Yeah. Okay. Good. Okay. I think that wraps up the questions. So if you have additional questions, anybody in the audience, you can send them our way via email, contact us on the website. The presentation will be made available after the webinar is over. Anybody who wants this will have it available as a PDF or a PowerPoint. There will also be a recording of the webinar that will go up on our website within a couple of days. Mike mentioned the survey at the beginning of his presentation. There will be a survey sent to you all afterwards. It takes about a minute to provide your feedback, which we would greatly appreciate. And then up here on the screen now, Mike's got the next 3 upcoming presentations in this series. 2 weeks from today, we'll be talking about integrated servo motors. I'll be leading that presentation. Then on June 4th, we'll go under the hood of closed loop step motor control. That will come from our CTO, Jeff Kordick. And then we'll have Mike back again on June 8th to talk about add-on instructions. I think all of those are going to have some really good content for everybody. So please be sure to sign up for those. And thank you everyone for attending, and have an excellent rest of your day.